Peekaboo, how are you? Welcome to this episode of Marshable Math. My name is Mr. Marsh. Today we're going to be discussing functions, and in particular function notation. So get some paper, pencil ready to go. We're going to have you do some practice problems later on. But right now, if you know about equations, you probably already know a lot about functions. If you remember from the last video, we defined a function as a relation in which there is only one output for each input. And so if you come across an equation, say y is equal to 3x plus 2, the question would be something along the lines of, well, okay, if x is equal to 2, then what's my value for y? And that's fairly simple enough, right? We come along here and we would say, well, I'm going to replace the x with 2, so y is equal to 3 times 2 minus 2. 3 minus 2 is, or 3 times 2 is 6, minus 2, we would say, well, that's really easy, y is equal to 4. So when x is 2, y is 4, that's the solution then to this equation. But what if we had another equation, also named y, and we said, well, y is also equal to 2x squared plus 1. If I said, what is y now when x is equal to 2, you have a little bit of a dilemma, because there's more than one possibility for what y is. I have this equation here and this equation here. Have you ever been in a classroom where there was more than one student with the same name? Like maybe in your class, whatever, there were two Billies. And so the teacher would ask Billy, oh, what is y when x is equal to 2? There's some confusion, because you're not sure which Billy you're speaking about, right? So don't you have to give them a second name or a different name? Don't you have to call one of them like Billy number 1 or Billy number 2, and then there's a fight because, you know, who's going to be number 1? Or maybe you call them by their last name, or you have to have some way of differentiating which one is the one and which one is the other. So that's the similar problem that we have here. Well, I got two different expressions that will give me a y value. Which one are you talking about? So what we need to do, just like in the classroom, is we need to give the equation, we need to give the function its own separate name. So instead of calling this one y, let's call it f for the function. And the letter that comes after f in the alphabet is g, so let's call this one now, let's call this one g. And so the question I might ask is, all right, so when x is equal to 2, what's f? Well, now I know that I need to come back over here and work this side here when x is equal to 2. I'm not interested in that one. So that's what we do when we talk about function notation. The first thing what we're going to do is we're going to give them separate names. You can have the function called f, or you can have the function called g. It doesn't really matter which letter it is. You can have a function called k or h or whatever it is. Just understand that it's a specific name. It means a specific equation. But there's more to it than that. If I came over here and I said x is 2 and f then is going to be equal to 4 from now on, that's still a little bit, it's too much, it's too wordy. It takes too much time and too much effort, and it's not efficient enough to say, well, when x is 2, then f is equal to 4. There's a more efficient way of saying that. So what we're going to use is what we call function notation. Function notation doesn't do anything different with the equation itself. The equation is still the same. But what we're going to do is we're going to say, instead of just f now, it's going to be f of x. And so maybe you've seen it there with like a parentheses with an x inside. This is red when you say this. This is f of x. And so over here I left the space for this one too in anticipation. This is g of x. What it means is that the function g here is dependent upon x. G is the kind of the output, g is the y in this case, and it depends upon what we do here with the x. So when I come through here and I say, well, let x is equal to 2, what I'm going to do is I'm going to say, well, it replaces this here. This is going to be f of 2 then is equal to 3, replace the x with the 2, minus 2, and so then in the end I say f of 2 then is equal to 4. And so very, very clearly what I can show here is that I show that I'm talking about the function called f. I'm telling you that the input to the function is 2, and I'm showing you that the value of the function at 2 is 4. So what we have going on here is this. We have f, and then there's a parenthesis, and then there's an equal. And so if I could use maybe a little color-coded thing here, what I've got is I've got f of 2 is equal to 4. What I'm saying then is I'm saying that the input value is here. This is what goes in. And this is what you then get out. So if I were to do the G now, I would say, well, what is G? Well, I would say G of 2 is equal to, now I'm going to use the relationship here that's G. G says what I'm going to do is I'm going to take the input and I'm going to square it and then multiply 2 and then add 1 to it. What's my input now going to be? Well, my input is going to be the 2. So G of 2 is equal to 2 times 2 squared plus 1. If I run that math then, let's see if I can do it right. G of 2 is equal to 2. So 2 squared is 4, times 2 is 8, plus 1, is that 9? I think so. So very clearly here I can say f of 2 is 4, g of 2 is 9. I know which function I'm talking about, I know what the input is, and I know what the output is. So that's really what we're talking about when we say function notation. It's still just y, it just means a specific y. It's the function g, or it's the function h, or it's the function f, or something along those lines. You might see something like this. Like in physics, we do something like the height of a diver depends upon the time, and so it would be, negative 16 t squared plus 5t, plus 10, or something like that. It's still just an equation that involves the input of time, and it says here the height is a function of the time. The height depends upon the time. Does that make sense? So it's a little fast shorthand to very quickly tell which function you're talking about, what the input is, and then also what the output is. So let me do an example here, or give you a demonstration to work along with me here. So let's go back and let's do this. You've got your equation, f of x is equal to 3x minus 2. So let's say now that I wanted to do, well, what is f of 3? That's how you'd write it. What I'm asking is, what's the y value of the equation f when the input is 3? So what I would do is I would take the equation here and I would say, well, it's 3 times an input minus 2 from it. And what is the input? The input is 3. So f then of 3, let's see if I can do this right, 3 times 3, which is 9, minus 2, 7. Very clearly there what it is. But what is g of, let's say, negative 4? Oh, I need to go back to the g. Oh, I erased it. Rats. Let me write that back up here again. G of x is equal to 2x squared plus 1. So g of 4, I know I don't want this one. I want the g. And I'm going to set up the structure 2 times something squared plus 1, negative 4. Let's see here. Negative 4 squared, that's 16, times 2 is 32 plus 1. So g of negative 4, I'm going to say, is equal to 33. Okay? Does that make sense? Always make sure that you use parentheses when you do your substitution in. Because if in the case of a negative here, you need to know that the negative is actually part of the base then when you square it. So let me give you a practice problem or two and we'll see how you fare. Okay? Again, using these two functions, here's what I want you to do. I want you to do f of negative 5. And I want you to do also g of, let's make it negative 1. Okay? So go ahead and press pause in the video, try your hand at these problems, then we'll compare answers here in a moment. Okay, what have you got? All right, so if I'm looking at f of negative 5, I'm going to come over here to this one. And I'm going to say then f of negative 5, that's equal to 3 times negative 5 minus 2. And I'm just going to simplify the right-hand side. So that's equal to negative 15 minus 2. Is that negative 17? I think so. So that is the value of f at negative 5. What about g of negative 1? Well, let's see. I've got then g of negative 1 is equal to 2 times negative 1 squared plus 1. Let's see here, negative 1 squared, that's positive 1, times 2 is 2, so g of negative 1, then that's equal to positive 3. Okay, how'd you do? Did you get those things? Hope so. One thing I need to point out here, though, is that folks often confuse this with multiply. they think that what this means is they think it means -5 times f is equal to -17. And they get to this level and they think, oh, I have to solve it for f, like f is just the y by itself. And that's not true. So if you see somebody doing, oh, I'm going to need to divide by -5 and divide this side by -5, that's a clear misunderstanding of what the idea is. This does not mean f times 5. It does not mean this down here. It simply says the output value of the function f when the input is -5 is equal to -17. Okay, so function notation. Here's a question for you. What if I said f of a? Because I don't have to have just numbers in there. What does f of a mean? Well, f of a says the function f, but instead of the input being x, I'm just going to let the input be a. That just means I replace every x in here with a and simplify if I can. Isn't that just 3 times a minus 2? Yeah? Okay. What if I said this? What if I said g of a plus 1? What would you do there? That one's a little complicated, but that one's very interesting. So try it. Catch up with the video on composition functions. So, function notation, here's the main idea. Conjunction, junction, what's your function? You got to know the difference. Name them differently, understand that it means input and output in a very precise language. Okay? I hope you're having a great day, and I hope you learned something. Talk to you later. Bye-bye.